The ocean is the most important part of the Earth's ecosystem. It absorbs up to 90% of the heat from global warming and produces over half of our oxygen. While we have a lot of data about rising ocean sea levels and temperatures, scientists have a lack of nearshore data, which would allow them to better understand how these changes affect nearshore ecosystems. Whereas in the open ocean, researchers can put a buoy or use satellite data to track ocean conditions, the dynamic nature of changing coastlines make it almost impossible to do the same for nearshore data. However, this nearshore data of interest is exactly where surfers go every single day.
The Smartfin acts just like a normal fin, but is a platform for instruments that you would find on NOAA buoys. Smartfin collects motion, location, time, and temperature data, and with this information, researchers can track temperature trends over time, as well as use motion data to learn more about wave patterns. Here is data collected at Windansea Beach during a longboarding session in July. We can see the fin adjusting to ocean's temperature and giving us data accurate to 0.1 degrees Celsius when it was calibrated. We can also see spikes in acceleration here and here, showing certain waves that I was riding, or times when I wiped out. Combining the 9 axes of movement, we can discern position and maximum velocity of a surfer on a wave, which can lead us to calculate the minimum wave height to produce those effects. Surfers can treat the Smartfin like a normal fin other than charging, making it easy for anyone to get involved in the Smartfin project.
This summer we have made several improvements to the system behind the Smartfin. An early problem we ran into was our inability to use the 3G fins. Since the fins relied on cellular networks to transmit data, our 3G fins were stuck in an upload state because wireless carriers have phased out their 3G. In order to solve this, we implemented setting a no upload flag. The fin would loop between its sleep state and charge state continuously even when water was detected. After fixing these 2 critical issues, we had a fin that was working mostly as expected. For the rest of the summer, we continued to fix bugs and add features to improve the fin.
To make sure that the fin gives accurate data, we need to make sure that all sensors aboard the fin are calibrated, most notably the accelerometer, the magnetometer, the gyroscope, and the thermal sensor. We can use the magnetometer to give us the orientation of the fin at a given time, since it measures the strength of the Earth's magnetic field in all 3 dimensions. However, before we can get reliable fin direction and orientation, we need to ensure that the magnetometer doesn't read a distorted magnetic field by calibrating it. We can offset the effect of nearby magnetic fields, such as those induced by electrical currents, and the effect of nearby ferrous material with corresponding transformation matrices. The calibrated readings were measured against video footage of a surf session and manually compared against a known calibrated compass. This is a typical surf session visualized on a compass, where the radial axis represents time in seconds.
The accelerometer is used to measure the acceleration along all 3 axes. Since the accelerometer can measure gravitational acceleration, to calibrate the accelerometer, the sensor was lined up in all 6 orientations and calibrated against the 1G vectors that were expected. The gyroscope measures the angular velocity along all 3 axes. There was no viable way to calibrate the scale of the gyroscope, so it was 0 calibrated. This type of calibration ensures a 0 reading when the sensor is not rotating.
To calibrate the temperature sensor, we put the fin in 3 different temperatures of water within the range people can surf. The fin reading is then compared to the temperature reading from an NIST calibrated SPE, the same model used on piers across California, including on Scripps Pier. By then running a linear regression of the relationship between the true temperatures and the fin's reading, we can determine and calculate the coefficients to be able to adjust the temperature. We needed a way to pot our electronics in a fin strong enough to withstand the forces of surfing using materials found in any lab. We decided we would make a core to house our electronics and then fiberglass that core for strength. This method allowed us to make a strong, responsive, and watertight fin that surfers would love. We start with a 3D model to house all of our electronics to act as our core. We then make a mold of an existing fin. We use silicone to model the bottom and top, and this will act to finish our final fin in the right shape. Fiberglass cloth can be easily cut to any shape, and when combined with resin, creates a very strong material. We used about 5 layers of fiberglass on either side, though we hope to use at least 15 in the future to make it way stronger. Here we can see the fiberglass in the mold holding the shape of the fin. Fiberglass cloth also allows you to push the pins through so that we can access them from the outside. In our next iteration, we're going to use a larger 3D core and 10 more layers of fiberglass on either side, as well as cure the fin in positive pressure to get rid of voids in the mold. This summer, we've put a lot of time and effort into documentation and simplifying the onboarding process as well as our tools and other pieces of our code base. We hope that these efforts can help new researchers more easily contribute to the project.